So the next one is a 90-degree rotation. 90-degree rotation would be counterclockwise about the center. Center is where the diagonals meet. So when you do that, you end up with this as your transformation. You can double check that this is indeed true. If 1 will move to 2, so you have 1 going to 2. I need to correct this. You should have 2 here, 3, 4, and 1. The same way we have here. So this what appears here is for the identity. I think I didn't change that. But what appears on this end is correct. So this column should be exactly the same as this second column here, where 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. And you can see it from the diagram. If you rotate it anti-clockwise through 90 degrees, 1 will move to 2, 2 will move to 3, 3 will move to 4, and 4 will move back to 1. And as a function, this is what it looks like. Now the next one we consider is a 180-degree rotation. And for this one, if you take through 180 degrees rotation, that means 2 90-degree rotations. So 1 will move twice, all the way up to 3. Oh, again, there's a problem here. So 1 will go to 3. I'll have to edit this before I share this. I share the slides with you. But on this end, it's correct. So 1 will go to 3, 2 will go to 4, 3 will go to 1, and 4 will go to 2. So on this other end, it's listed correctly. So you can use that as the answer. But I will edit this before I share the slides. So we call this transformation A squared. The one for 180 degrees positive rotation. Positive rotation simply means the rotation is anti-clockwise. So the other one is 270 degrees rotation, or 3 over 2 pi. So this one, it means you have to go through 390 degrees rotations. One of them is that. One goes to, if you do it 3 times, 1 will end up at 4. So you have 1 goes to 4. Again, I will correct this. This part is wrong. Follow this, the last column. That's the correct assignment. So 1 will go to 4, 2 will go to 1, 3 will go to 2, and 4 will go to 3. So how you see that is this. If you take this through 270 degrees rotation, 1 will move all the way to 4. 2 here will move all the way to 1, and so on. So that's how it works. And then as a function, this is what it looks like, and we call it A cubed. Again, this should be A, not R. This is A cubed. The slides have some errors, but take note of that. So this is the last of the rotations. You can't do any more rotations. The next rotation here maybe will be 360, but that one will be just like the identity map. It doesn't change anything. We already have the identity map, so that would not add any new symmetry. So the next ones we consider are the reflections. So the reflections that will give us a symmetry are the ones, the first one is the one that this vertical line that bisects these horizontal sides. So if you reflect along this line, if this is your mirror line, 3 and 4 will be switched, and also 2 and 1 will be switched, so that 1 will go to 2, and 2 will go to 1, 3 will go to 4, and 4 will go to 3. So I'll have to edit all this before I share. But now note that the correct map would be on the extreme right here. The assignment, the correct assignment for each of these elements is on the extreme right. So this should be easy to see. That's for the first reflection. You can still hear me?
Yes.
Yes.
Good.
Yes.
So we continue. So the next one we look at is now the reflection through this horizontal line. And here 4 and 1 will be switched. So 4 will come down and 1 will go up, right? So it will switch 4 and 1. And it will also switch 2 and 3. So that 1 will go to 4, 2 will go to 3, 3 will go to 2, and 4 will go to 1. So this gives you the horizontal reflection. We can also have a reflection through the diagonals, like that. Now the first diagonal we'll consider is the one that passes through the vertices 1 and 3. And since the vertices 1 and 3 are on the mirror line, they don't move at all. So 1 and 3 will remain fixed. But if you reflect, 2 will move to 4, and 4 will move to 2. So 2 and 4 will be switched, but 1 and 3 will not move. So 1 will go to 1, 2 will move to 4, 3 will move to 3, and 4 will move to 2. So again, notice that 1 and 3 will remain fixed, but 4 and 2 are switched by this transformation. So that's the first reflection along a diagonal, and we choose to call it D. So this, we shall call it D. That's the name of this function. So the next one is the second diagonal. This is a diagonal that passes through the vertices 2 and 4. And if you reflect along this diagonal, 4 and 2 are on the mirror line, so they will not move. But 1 and 3 will be switched. So you can see 1 and 3 will switch places, but 4 and 2 remain in the same place. So you can see 4 is fixed, 4 goes to 4, 2 also goes to 2 because they don't move, but 1 goes to 3 and 3 goes to 1. So this gives us a last transformation. And we have been able to write all of them as functions as well. And once you have them as functions, now you can forget about these diagrams and simply work with these functions. Once you have these functions, you can now study the group. We haven't shown that it's a group, but we just, for now, you have to believe it's a group. We shall go through as we go along, you will see, you will be able to check that it's a group. So we represent the set of all the symmetries as this. We had, I've written A twice. I need to delete one of them. We need only one of them. So there's A squared, A cubed, B, C, D, and should be G, right? Yeah, it should be G. We use G up here. So this should also be G. This one here should be G. And then we remove one A so that we have a total of 8 elements in this set. So under composition of functions, this will form a group. In the next slide, we look at some of the compositions using the same ideas. This is D4, not D3. This should be D4. And this is D4 also. This is D4 as well. So take note of those corrections. So this should be D4. That is D4. And this is also D4. The 4 is supposed to, because it's a square and it has 4 sides, that's why we have 4. 3 was for the equilateral triangle. We had 3 sides, and that's why we had D3. So here is one composition. If you get the composition of A and B, simply means B will act first, followed by A. And when you work it out, you end up with G. Remember, G was the diagonal, the reflection. I think it was going through 4 and 2, the diagonal going through 4 and 2, which leaves 2 fixed and 4 fixed, but interchanges 3 and 1. So that's G. When you compose A and B, you end up with G. You eventually have 1 going to 3, 2 going to 2, 3 going to 1, and 4 going to 4. So you can double check that this is true. Try to quickly double check that that is true. So as you double check, I can see if there are any new people trying to join. I can let them in. Quite a number of latecomers. Okay, so we're back. Have you confirmed that this is correct? We can go back to the functions if you did note them down. Has anyone confirmed that this composition is correct? Can you hear me?
Yes.
Yes, it's correct.
Yeah.
Yes.
You confirmed. Okay, that's good. So we can proceed. So you will have to do a lot of practice with these calculations to get used to them. So make sure you go over them again later. The video will be made available after the class. So for now, try to do as much writing as possible as well. So make sure you have your notebook and your pen as well. Don't just stare at the screen. It's very difficult to learn mathematics by staring. Good. So using the same ideas, you can fill in the group table for D4. I have filled in some of them. Hopefully they are correct. You can go and double check this. And then you fill in the remaining spaces. You compute all the others and fill them in. So I've given you some work to check here. And you will notice that any composition with this E leaves the other elements intact. And therefore, this element E will act as the identity. So check all these computations and also try to fill in the blanks in your own time. So this will give you the multiplication table for D4, or the group table for D4. So remember how it works. The composition starts from the column side, moving towards the row. So whatever appears, for instance, what appears here is A squared composed with B in that order. This C here should be the result of composing A squared with B. So A squared, and then you have the small circle and B. So you have, if you are to write it, it should be A, then the small circle, then B. So what that means is that B will act first, followed by A cubed, because that's how the composition is defined. The function that appears on the right-hand side will act first, followed by the one on the left-hand side. Any questions on that? No questions, okay, so we proceed. So the other things we can note are the following. The inverse of A is just A cubed. If you go back to the table, if you get A and A cubed, you get the identity. So it means the inverse of A is just this A cubed, like that. The inverse of A squared is itself, because if you go back to the table, if you have A squared and A squared, it gives you the identity as well. So A squared is its own inverse. And we can find the inverse of all the other elements. B, C, D, and G are all their own inverses. So the inverse of B, the inverse of D is D, and the inverse of G is G. Now, if you look at the table carefully, you can observe that all the elements can be written in terms of A and B as follows. Let's go back to the table. So you see, I can write the first three are fine, A squared, and A cubed. Those are all in terms of A. So to get A squared, you compose A with itself. To get A cubed, you compose A with A squared, so on. So everything here is fine. And then B, we want to write them in terms of B. So we pick B first on its own. Then we show that the remaining three can also be written in terms of A and B. So if you check A and B, you will get G. A squared and B, you will get C. And then A cubed and B, you will get D. So this gives you all the elements of D4, but all of them written in terms of A and B. That is sometimes convenient, and therefore we can write all the elements of D4 as follows. We have E, A squared, A cubed, B, then AB, A squared, B, and A cubed, B. So this is another convenient way to write the elements of D4, and it makes it much easier to study when they are put in this form. A few more observations. You can check in your own time that if you compose B, A, and B, that order, so this means you have a compose. If you were to write it, there's some shorthand I'm using here. So instead of, let's just go back here. You notice here, when you're doing the composition, we have this small circle in between to denote the operation of composition. So most of the time we shall just write this as AB and omit the circle. A followed by B next to each other, and we remove the circle to represent this operation. So that's what I'm doing in this section. I've removed that circle and just written the operation multiplicatively. Is that making sense?
Yes.
No.
Yeah.
Pardon?
No, for that one, also that for B composed with A composed with B.
This is just composition of three functions. You have done this in SMA 101. So basically it means you will, if you go back here, okay, I don't have a diagram from B. So suppose you have A composed with B, composed with C. So what will happen is you will have another row here for C, another column for C. So C will take 3 to, I can't remember where C takes 3. But now C will act on this. So if you have A, B, C, no, remember the order is from right to left.
C.
So if you have A of B of C, then C will act first, followed by B, and then followed by A. So the last, whatever you get here as the last column, will give you the new elements that you have obtained through that composition. Does that answer your question?
Yes, it is.
So remember, the order of operation for composition is from right to left. The rightmost function will act first, and we'll move towards the left after that. So this one you'll do in your own time. Do that composition and confirm that if you compose these three in that order, B, A, B, you will get A cubed. And this A cubed is just the inverse of A. So you could write this as B, and B is its own inverse. So this statement can also be written as B inverse AB is equal to A inverse, because A cubed is the inverse of A. I think we saw that up here. So there are a number of ways you can choose to write it. So this is, sometimes this is convenient. And you can, so from this relation here, you can multiply both sides of this equation here on the right by B. If you multiply by B here, you will get B squared, which is just the identity. That means if you have the identity on this, it's the same as B inverse A. And then on the other, since you're multiplying both sides by B, on this other end, you'll have A inverse B. So this means that BA is the same as A inverse B. You could also write A inverse as A cubed. That would be fine. You could write BA is equal to A cubed B. So using these properties, it's possible to now multiply any of these elements and obtain and reduce the product to one of the elements already listed here. We do an example. We did an example yesterday. Here we shall multiply AB with itself. If you multiply AB with itself, it's the same as A. Since this composition of functions is associative, so I can put my brackets anywhere I want. So I know BA is the same as A inverse B. A inverse B is here. BA, using this, I can replace BA with A inverse B. But I know that if I multiply A by A inverse, I will get the identity, which is what I have here. And I know B is its own inverse, so B multiplied by B will also give me the identity. And the identity multiplied by itself will give me the identity. So the product of these two simply gives me the identity. So in your own term, you can also double check that this product will give you A cubed. If you pick AB and multiply it by A cubed B, A squared B, sorry, you will get A cubed. So you can, in this form, you can actually compute using these properties. You can get the product of any of these elements. Product here means composition, and you reduce it to one of the elements already in this set using these properties. So you can try this on your own in your free time, and you rewrite this table now in the new form. Instead of B here, sorry, instead of G, you should have you should replace, for instance, G should be replaced by AB, C should be replaced by A squared B, and D should be replaced by A cubed B. So you can redo this table now with the elements of D4 renamed like this, and try to fill up the whole table in that form. So that is what you have been requested to do in this last statement. Any questions on this? Can you still hear me?
Yes.
Yes.
Oh, but you have no question. Hakuna maswali.
Excuse me, mwalimu.
You are excused.
Hapo juu bado nachanganya kidogo.
Wapi juu?
Is equals to A cube. Kija hapo mbele unapata B inverse is equals to B, C inverse is equals to B.
Now you need to go back to the definition of a group. Did you do SMA305?
Yes.
And you don't recall anything of this sort?
Nilikuwa nayo mimi andika.
So these are the elements of the group, right? Let's go back to this set. Remember here, A has been written twice, so I will delete this before I share. And this last one should be G. So I will edit that before I share. So now, in a group, every element has an inverse, right? And what's the inverse of the element? The inverse of A is the element which, when multiplied by A, will give me what?
The identity.
Yes.
Identity.
So if I multiply A by A cubed, I get the identity. That composition gives me E. E is the identity. So that means the inverse of A is A cubed. Does that answer your question?
Yes.
Similarly, if you multiply B by itself, because it's a reflection, if you reflect twice, you go back to the original square, right? So it's its own inverse. The same with all the other reflections. And also this 180-degree rotation is its own inverse. A squared multiplied by itself will give you the identity. So you can try this on your own. You try to do fill in this table. This table will give you all that information. Are we together?
Yes.
Yes.
So here we are just going to use a notation that is used for groups. The notation for the inverse of an element is usually A negative 1. If the group is written, the group operation is written multiplicatively. So here we're just trying to use the notation for inverse. The inverse of A squared is itself. The inverse of B is just B, because when you multiply B by itself, you get the identity and so on. So it's important that you go back to the definition of a group and master that definition. You will have to carry that definition along with you throughout the course. So if you don't remember it, some of these things will not make sense. So with the help of these defining relations, it's possible to study D4 without referring to the actual functions or even the diagrams that we're drawing. Once we pull out those relations, we are able to we're able to write D4 in this form, and then we can get products of any elements inside here just using these relations. So we no longer need the function, and we no longer need the diagrams now. So and that means we can just study everything algebraically now. And that's what we stated here. So eventually what the only things you need to construct D4 are these two elements, this rotation, the 90-degree rotation, then one of the reflections. And you notice that the rotation raised to 4 gives the identity. And this property that AB is equal to A cubed. Now all this will enable you to construct all the other elements in D4 without having to bother with the diagrams or the functions. The same, you can do the same for D3. D3, we also noted that you only need these two elements to write out all the remaining four elements of D3. So, and then along with these properties, you can construct all the other elements of D3. So this A and B are usually called the generators of the group. And we shall explore this in more detail later when we talk about generators. So that brings us to the end of today's class. Are there any questions? So now there's also, in the folder I shared, there's a set of typed notes. And at the end of each chapter for that notes, you have a lot of practice questions. So take time to do those practice questions now.